So let's try to explain this structure a little bit better, where we are looking at the relative humidity being 85% everywhere, but specifically, why does it drop off despite being pumped with humidity from near the surface via this convective processes that should bring up the water vapor into the upper atmosphere. Okay, here it is, the best way to explain. So we talked about deep convection cumulonimbus clouds, which have strong vertical motions, convergence of water vapor near the surface to replace the rising air. So obviously humidity is being transported upwards. That's part of the process that drives the rigorous vertical motions, because as air rises, expands, it cools, water vapor condenses, releases heat of condensation, drives further motion upward, driving clouds all the way to the top of the troposphere and creating these anvils because of the upper air, right? So there is vertical advection of water vapor, but you have, when you talk about relative humidity, it's always about specific humidity divided by saturation specific humidity. So saturation specific humidity changes with temperature, and relative humidity obviously also changes with temperature, but relative humidity also depends on where the moisture is. Specific humidity also depends on how the moisture is being supplied by advection or by evaporation near the surface and so on, right? So you have saturated updraft, but as it rises, eventually it's saturating and it's raining, so it's losing moisture. That's the whole purpose of the process of creating rain, right? You transport a lot of moisture up, you condense it, and you dump it back, and you are advecting out drier air. It is depleted of moisture. It's colder, so saturated specific humidity is lower, but specific humidity is also lower. Temperature effect dominates, so you have low relative humidities up here, and that low relative humidity air is going out in these outward branches, and it is sinking here, and this descent is dry. Okay? Why? As I said before, because this air is slowly sinking, it's compressing and warming, as opposed to the rising air which expands and cools. The sinking air compresses and warms. The buoyancy doesn't go up because it's a cloud-free region mostly, except for some cumulus clouds, so there is a lot of radiation loss, which is a slower process. So net result is that there is a slow sinking as opposed to very rigorous fast upward movements. Remember, in the cumulonimbus we said it can be tenths of meter per second or 25 meter per second, for example. These are slow sinking, but as it compresses and warms, saturation specific humidity goes up, because ES is a e to the beta T. T goes up, saturation vapor pressure goes up, and relative humidity goes down because it has lost its its moisture, and specific humidity is low, so relative humidity is low. So this is the cell that we will look at next, the so-called Hadley cell, and we will add a little bit more details. For example, air here is actually converging from colder subtropics to warmer tropics. So is it really transporting energy poleward that we said is needed for balancing the energy distribution? Of course not. But there are moisture processes, and remember we defined the moist static energy as CPT plus GZ plus LQ. We'll come back to that and see that even though here transport is actually towards the warmer tropics, net transport because of moist processes is still poleward. This is where moisture becomes so critical, right? Even though specific humidity is small, relative humidity is small, and so on, and moisture amount itself is few grams per kilogram, moisture is very critical for atmospheric circulation processes and for energy transport. Okay? Energy transport is accomplished greatly by evaporating from the ocean, taking energy out, condensing in the atmosphere, and driving circulation as well as transport of moisture and moist static energy. All these things matter.